Hi everybody, this is Mark Weitzman, and welcome to my YouTube channel and my course on quantum field theory, a student's perspective. Today I'd like to start something different because this effective field theory course has started again on MIT X Online, and it's an excellent course, but it's very advanced. It assumes you know quantum field theory and prerequisites, like it says, a graduate level course in quantum field theory, and it assumes that you're familiar at the level of Peskin and Schroeder or Czernicki, and it just assumes a lot of knowledge, which I when I've signed up in the past, I haven't had that knowledge. So I'm going to try again, and as part of that, I'm going to review and reread the books Peskin and Schroeder and Czernicki. You can see them both above me, Peskin and Schroeder in white, Czernicki in green. Now, the interesting thing is that the book Peskin and Schroeder has a reputation. So what I'm going to do in this blog is every day as I review a chapter or so on and I find something noteworthy, I'll make a video. They're not going to be complete lessons like my previous videos. They may be like 15 minutes or a half hour. But I just want to summarize some of the stuff that I've studied that day and some of the fine points. Peskin and Schroeder, this is the web page for Peskin and Schroeder's book, and it has corrections on it. Can't see it, but there's a link to corrections there, and has a reputation of being a difficult book. These are the corrections to if you get a recent edition, most of these are already in there, but there's definitely a lot of corrections, and this only has some of them on this page. There's also a complete solution to the problems. I recommend not looking at these things, but they're online and you can find it, and he's got like 200 pages of typed solutions to the problems. But if you don't work out the problems yourself, you're not going to learn that much. In any event, the book has a reputation of being a difficult book, but it's not really that difficult. What it is that it's a little bit unorganized at times, and sometimes it shows you things ahead of time. So chapter 1 especially, people start on chapter 1. Usually chapter 1 of a book is a very easy chapter, but here it's like they start with a heuristic overview of scattering, electron positron going to a muon anti-muon, and people look at this and they say, what's going on there? Where did this come from? I don't understand any of this. I guess this book is beyond me. But actually, if you've had a good undergraduate quantum mechanics course and you're comfortable with classical physics and everything, you should be able to understand everything that he does in chapter 1. But I'm going to try and explain to you some of the fine points which some people don't ever get. First of all, he starts off with he just out of nowhere, he puts down this equation for the cross-section. Now, he's going to derive this later in the book. But just to show you right now, all that's going on is there are some constants here which irrelevant. But here, what's important is this, and this is the matrix element. So this is what's really important in QFT. This is just kinematics and dynamics and cross-sections, which he'll go through later. But just to show, the important thing is that it's dimensionally consistent. The dimensions of a cross-section, which is a length squared, an area, and the dimensions of d omega is equal to angle, is just 1. The solid angle is 1. So the left-hand side has dimensions of length squared. The only thing that has dimensions on the right-hand side is the energy, center of mass energy. And the dimensions of energy We're working with h bar equals c equal 1 convention, which is standard in high energy physics and quantum field theory, so you should try and get used to it. But obviously the dimension of energy is, mc squared, but we have this c squared is equal to 1 by our units. So this is just equal to the dimensions of mass, but the dimensions of mass, energy is mc squared, right? So the dimensions of mass is 1 over length. This is just, you could think of the Compton wavelength, h bar over mc. Let's say L Compton. Again, we're working in units with these R1, so it's just 1 over m. So you should be familiar with, from quantum mechanics, that length and mass are inverse. So the dimensions on the right-hand side is 1 over L squared is L squared. And over here we have L squared. So it's dimensionally consistent. So that's where that formula comes from. The 64 pi squared and everything, you're not going to worry about in this chapter. So he sets up the problem. This is all in the book, but I'll rewrite it. We have an electron, and it has a momentum p. And we have a a positron. And this has a momentum p prime, but it's going the other direction. And we're working in the center of mass, so we'll be working in a system where p prime is equal to minus p. And then they go fly off into muons. This is mu plus, and this is mu minus. And this is the scattering angle theta. And in this book, they usually use the convention of the z-axis as the axis that the particles originally came flying in at. P prime is minus p, and conservation of momentum and energy give you k prime is equal to minus k. We're working in this chapter with a very, very simple, we're going to work with the rest masses, so we'll think of working at very, very high energy. The rest masses of the electron and the muon are 0, so they won't factor in there, and we don't have to keep them into account. And so the magnitude of P, which is equal to the magnitude of P prime, this is going to be equal to the magnitude of K prime, is just equal to the center of mass energy over 2. That's the definition. So that's the kinematics that we're going to start with. And then he draws a, we're going to be working in perturbation theory. So it's kind of like just standard quantum mechanics. You can imagine a Hamiltonian, which is equal to H0. This is like the free Hamiltonian. And then plus the interaction Hamiltonian. And this is going to be the perturbation in the interaction representation, which we'll talk about later if you haven't seen it in your beginning quantum mechanics class. And he draws a Feynman diagram. Obviously you're not supposed to understand everything about this, but some of you have may seen it before. You can think of, by the way, there are many different ways of drawing Feynman diagrams. Some have time, usually they go from left to right, except in Coleman's book where they go from right to left. And most of the books, time goes up and space is horizontally, but some do it the opposite. So for the most part, you should think of these in momentum space and not even worry about space and time. Anyway, there's an electron, there's a positron, and on Feynman diagrams, the arrows on the lines, at least for QED, represent charge. So this is the flow of charge. So we're thinking of like negative charge is actually positive charge is going forward, so it's as if negative charge is going backwards. The only important thing is that the momentum is this way, and P prime is this way. So it's two particles that are going in, intersecting. They collide. Now you might think we could go right into muons, but the first order matrix element is 0, since electrons don't couple directly to muons. Okay, they couple through photons. So going back to the Feynman diagram, we can think of the electron and the positron coming together, and all of a sudden they make a photon. And we can write down the photon momentum, think of it as flowing this way, and Q is equal to P plus P prime is equal to K plus K prime. Now I know some of you are going to say, well, in the center of mass, that's 0. How can a photon have 0 momentum? If a photon has to move at the velocity of light, it can't stand still. Well, this is a virtual photons, and virtual particles, as you may remember from quantum mechanics, or as you'll certainly learn in quantum field theory, they can do anything. They don't have to be on what's called the mass shell. So this is a virtual photon. And then it decays, or it makes, 2 muons. So again, this is mu plus, and it has its charge always going opposite because it's a positively charged particle, but its momentum is actually, going that way, and then the muon is going this way. So this is a typical Feynman diagram, and these things with the big circles are called vertices. And what you really want to do is you put these together. There are interactions. Interactions occur. We're not going to discuss that much now. Interactions occur at vertices. So for QED, the interaction is minus IE gamma mu, where gamma mu is a Dirac matrix. Again, don't worry about this because we're not going to use that in this calculation. And then the lines, straight or curvy, represent propagators. So something like this, if we want to know the probability amplitude of going from this point to this point, it's going to be some kind of propagator, and we might call this, like, let's say this is mu, and this is like x mu and x nu. And we might call this, for a photon, like d mu nu, and for an electron we might call it s mu nu, and so on. So we get certain propagators, which are, we'll derive them. For an electron, it's something like, 1 over p slash minus m, and then for a photon, it's like 1 over k squared, and for a scalar particle, it's like 1 over k squared minus m squared, so on. K is the momentum. So we'll get to all that later, but everything on this Feynman diagram represents a factor. And at this point in time, you're not really supposed to understand any of that, because the whole idea of this chapter is just to show you how just using old-fashioned quantum mechanics, second-order perturbation theory, we can almost get the answer. So Peskin and Schroeder, they write down the matrix element. They use a squiggly m. I'm just going to use m. And they say it's proportional to. They basically say the final state is mu plus, mu minus. There's some kind of interaction at the vertices. We have an intermediate state, which is a gamma, which this is the summation. Gamma, gamma. Hi again at the vertices. And E plus, E minus. Again, standard quantum mechanics. This is in. This is out. This is like sum over intermediate states. Now, what's not clear, I mean, you're probably aware of it, but the photon is a vector particle. It's not a scalar particle. So we take that into account. We put an index mu up here and an index mu down there. So these are going to be like vector matrix elements, and we're going to take a special relativity dot product to get the total matrix element. And so this is what we're trying to calculate, or at least get an idea of the feel of it is. And what Peskin and Schroeder say basically is that what we need to do, what we're doing here is we need to conserve angular momentum. We come in with a certain angular momentum, and we end up with a certain angular momentum. Excuse me, I just got a phone call. I just want to see it. Okay. And so the angular momentum has to be conserved. And just to draw the diagrams they have in the book are a little confusing, and it's very, very hard for me to draw them. You might want to look at my picture here, but I'm going to try and say it how it works. So we have an electron. We're going to take a right-handed electron. So what does a right-handed electron mean? It means when you put your right hand around the, think of it this way. This is the electron. You put your right hand about it. Your thumb points in the direction of motion, and this thing curls around with the right hand. So that's what he means by saying it's going essentially from over here like this in front of it to there. This is a right-handed electron. And the positron, so the electron, we're taking a state where the electron is right-handed. And we're taking the muon, the positron, I'm sorry, to have the opposite handiness. So I'm going to draw the muon like this. And again, you could see this pencil. If I grab it with my right hand and do it, it's not because it's not going in the right direction. My thumb, oh, the picture's reversed because of the camera. That's not good. Okay. Anyway, we need to have it where, since the electron is going to the right and the positron is going to the left, if we have the electron left-handed and if we have the positron left-handed, we have this right-handed, then this one will have like an angular momentum this way. Let's call it J. Let's call this the z-axis. And the positron will also have the J that way. So we're going to have like J equal 1/2 and J equal 1/2. And the total J will be equal to 1. So because this is positron is going in the opposite direction, its handiness is the opposite of the electron, but they both have the same angular momentum. Now, so we represent that okay. And then with the muon, we do the same thing. It's just rotated. And we want the same thing with the muon. We want the mu minus to be right-handed and the mu plus left-handed. Doesn't have to be this way. This is just one example of what the possible spin configurations are. But so if we do this, we're going to get that the electron, the polarization vector for the electron, is going to be 1I, 0. Now, a lot of students see that and they say, where did that come from? I have no idea what they're doing here. But actually, they've seen this before, and I'm going to show you where it comes from, because some people don't remember this. So this is a page from Jackson's textbook, Classical Electrodynamics. It's also in undergraduate books in electrodynamics. And I'm just going to copy down some of the equations. So a linearly polarized wave is something like this. This would be a linearly polarized electromagnetic wave, assuming that, E1 and E2 have the same phase. This would be linearly polarized. Now let's say we want circular polarization. Well, as you can, if you read along in Jackson, it's just a phase difference, a 90-degree phase difference. So this is going to be like the same magnitude, otherwise we'll get elliptical polarization. Epsilon 1 and epsilon 2 are unit vectors. Let's say this is x, y. This would be E1, E2. You could call it EX or EY. These are the polarization vectors for a wave traveling in the z direction. But if we want to get circular polarization, we use plus or minus I E2 times e to the I kx minus omega t. So if you were to take what the real and imaginary part, remember in electromagnetism, the component is always the, so I'm just writing down here what these polarization vectors are. For a linearly polarized wave, as I discussed, and now for a circularly polarized wave, we have this, circular. And, if we were to describe this, we would say the x component is equal to E0 cosine kz minus omega t, and EY would be equal to minus plus E0 sine kz minus omega t. And if you were to graph that in the xy plane, imagine you had this is the z going out of the page, the z-axis, so x, y, z, and you would see that the electric field happened. Anyway, the electric field, E, would be rotating like this, counterclockwise in that plane, if you look from the wave approaching you. There are different conventions, but this one has it where the angular momentum is going to be in the z direction. J is equal to +1 in the z direction. So, so you can see that the E vector, just giving its x, y, z coordinates, is equal to E1 plus IE2, which is 1, I, 0. Now, if we were to write this relativistically, the time doesn't add anything to a polarization, so we would write epsilon mu equals 0, 1, I, 0. I don't think Peskin and Schroeder explained that well. That's why some people get really confused. But this is a circular polarization vector over here. And this is the relativistic generalization. Doesn't add anything, it's just the time component of 0. Now, if we want to do for the muon, you know, this is the electron. Let's say this is the electron. It's going this way. Let's say this is its polarization. Now, the muon is going off like that. So the muon has the same polarization as the electron, but it's rotated by like theta. So we need to rotate by theta about, and remember the convention, this is the z-axis, and Peskin and Schroeder call this the x-axis, which means by the right-hand rule, this is the y outside of the paper. We need to rotate by theta about y from z to x, which is the positive sense. Now, the only question now is how do you get the signs right? Every book does it differently. I'm doing active right now. And here's how I'm going to get the signs. I'm going to show you how to get the signs exactly like Peskin and Schroeder got. If you were working in the xy plane and you rotated a vector like this from here to here, and this is like theta, this is the matrix you would use. Cosine theta minus sine theta, cosine theta, 1, 0, 0, 0, 0. Now, how do you know this? Well, take a vector that's just has an x component, okay? After you rotate it, if you multiply that by like 1, 0, 0, after you rotate it, it's going to have like cosine theta as the x component. That seems about right. And the y component is going to be sine theta. In other words, it's going to start out here with an x component and no y component. Then it's going to rotate. It's going to develop a positive y component. So, so this seems right. Notice the 1, 2 component of this matrix is negative. That's the sign. That's what you have to remember. Now, we're working where we're rotating around the z-axis. I'm sorry, we're rotating about the y-axis. So we're going to have 0, 1, 0, 0, 1, 0. We know that. We know we're going to have on the diagonals the cosine theta and the cosine theta. It's just a question of the sign. Well, if the 1, 2 component is negative for, you know, it's always, you know, you remember 1, 2, that corresponds to 3, 1. So the 3, 1 component is negative. for a y rotation. So the 3, 1 is going to be minus sine theta, sine theta. And then we multiply this by the polarization vector that we had for the electron. And this is equal to cosine theta I minus sine theta. This agrees with Peskin and Schroeder. So we're using the same kind of sign convention. So now to get, so we have, so now we have gamma hi u plus mu minus, let's say mu is equal to E times, remember the time component is the first one. That's the confusing thing where people get confused. Cosine theta I minus sine theta. Okay. So the matrix element, to go from a right-handed electron and a left-handed positron to a right-handed muon and a left-handed, I'll call this E minus, E plus. I keep doing that. I'm so used to writing minus 1. E minus, E plus. This is mu minus, mu plus. This is going to be equal to, we take the E 0 comma cosine theta comma minus I comma I'm sorry, that should be, well, okay. When we take the dot product of the matrix elements, the muon is like this way. It's Hermitian conjugate. So we have to take the complex conjugate of what we had. So that's why the I goes to the minus I, minus sine theta. And then we take the 4-vector dot product of special relativity, E 0, 1, I 0. So this is equal to E squared. Now remember, the convention in this book is using a metric of 1 minus 1 minus 1 minus 1, so spatial components are negative. So I have cosine theta times 1, but it's negative, minus cosine theta. Then I have I times minus I is 1, but I'm sorry. So I have minus 1. And so this is equal to minus E squared 1 plus cosine theta. Okay. Now, as will be made clear later in the book, but Peskin and Schroeder mentions it, photon states, they do not couple with the zero angular momentum state. Like an RR or an LL, that's what they would have. You can think of the photon as being helicity or angular momentum is along or opposite direction of motion. Now, this is sort of a hand-waving argument, but he'll verify this later. It's hand-waving because we have virtual states, so it's not so clear that a photon has to obey our usual rules. Plus, why can't it be in a superposition? And so it's not obvious that it's not going to couple with zero angular momentum states, but it turns out that's correct. So there's only there are only 4 non-zero amplitudes. we have M RL goes to RL, which we worked out above. By the way, when I put equals here, obviously I'm leaving out some constant factors. It turns out this equal is right, but we have to show that there's no other factors. Then there's also MRL goes to LR, and this is going to be minus E squared 1 minus cosine theta. I didn't work it out. If you do the same thing with the spins, basically it's like the angles change, and that's why we get a sine here and everything. So you can work this out by yourself to make sure you understand why we get that minus sign here. And then MLR to RL, it's the same thing. 1 minus cosine theta. And then finally we have LR goes to LR. It's the same as we had originally, minus E squared 1 plus cosine theta. Again, these are the initial states, E minus, E plus. These are the final states, U minus, mu plus. Now, even if we don't measure the polarizations, the final states are distinguishable. So by the usual rules of quantum mechanics, we have to take the absolute squared of the matrix elements, and then we have to sum them over all possibilities, which is 4 of them. And then we we don't know what our initial polarization be. It's equally likely to be any of these things. So we divide by 4 to get the average cross section. Because 1/4 of the time will be in this state, 1/4 in this, and so on. So each of these is going to occur 1/4 at a time. So this is a general rule in quantum field theory. We sum, for computing cross sections, we sum over final states, the m squared, and average over initial states. So in this case, we're going to get m average is equal to 1/4 the sum, the absolute value of m squared is equal to 1/4 e to the 4th 4 plus 4 cosine squared theta is equal to e to the 4th 1 plus cosine squared theta. And then using alpha equal e squared over 4 pi, we get that finally, substituting in the formula we had originally, 1 over 64 pi squared ECM squared, 16 pi squared alpha squared, 1 plus cosine squared theta is equal to alpha squared over 4e CM squared, 1 plus cosine squared theta. And if we want the total cross section, we just integrate over all the angles, 0 to 2 pi of d phi, 0 to pi sine theta, d theta of d sigma d omega. And this is equal to 4 pi. You can do the integration yourself. Alpha squared over e cm squared. So the important things to take away from this is it helps you understand a little bit about what's going on. This is only the second order perturbation with zero masses for ME and MU. So with a little bit more work, you can put the masses in there and so on, and they'll do this later in the book, the full calculations. But you could see that You know, and they talk about in the rest of the chapter all these things about Feynman diagrams and vertices minus IE gamma mu, you know, like E minus, E plus. And we did like a photon, and we did that, you know, U minus, mu plus. But what happens if we like do something like this? Then we put a virtual electron E minus, E plus pair over here. This is going to be fourth order now. You know, actually, I'm not sure the exact order. Let's just say it's going to be higher order. And the idea that will actually diverge, except we'll renormalize and make it finite. So these Feynman diagrams are extremely useful in quantum field theory, as you all know. And we'll get like a recipe for doing these things. But the first chapter, they just want to show you how it's not too far away from old-fashioned perturbation theory and quantum mechanics. So thank you for watching this video, and I hope you know, maybe later today I'll add another video on chapter 2. Thank you very much. Bye bye.